SwayamPrabha. Digital India. Educated India.
Coming back to our discussion on this problem. So this is about that membrane problem, which is in the shape of a rectangle. And then what we have chosen is that psi naught is 0 because the m psi naught plus f g has to be 0. So g is 0 anyway, so psi naught is 0. And then psi 1, psi 2, psi 3 have been chosen to be the symmetric functions about x and y axis x. And we have chosen the values here. The cos function, which is the lowest trigonometric function, which is symmetric about x axis. And then similarly, this is about the y is equal to 0. And then this is the next term, which also shown. And so like this, we can take all the possible products. And then we can calculate all those algebraic equations, which is in the form of the matrix K multiplied by vector A is equal to vector B. And so the Kij is the 1, and the integrals here is that x goes from -2 to +2, and y goes from -1 to +1. And let's try to expand this one further. And psi I, and L is nothing but rho square by rho x square. And here psi I is psi j. Okay, so depending upon what we require, K11, we use psi 1 and psi 1 here. And let's just see. So for example, if you want to K11 is -2 to +2, -1 to +1, and psi 1 is cos pi x by 4 and cos pi by 2y. So this is psi 1. And then here derivative has to be taken on the same thing, psi 1, so which is cos pi x by 4 and cos pi y by 2. And here the d omega here is nothing but your dx dy. Okay, so continuing this one, so we have as you can see here, so this is operating on this one, right? So this is operating on this one. So we still have almost the same term as it is here. So essentially what we have here is that a second derivative of x on this one. So that means that it is pi by 4 square, right? Minus pi by 4 square. And so similarly, we also have here about y. So it is pi by 2 square, right? And this comes here, and then as well as this comes here, right? So we have and cos phi y by 2. Here in this case, it is the same thing. So we can also put squares here and dx dy. So performing all these integrations, I'll just straight away give you the pi square 10 by 64. I think there's a negative sign here. There's a negative sign here that comes here. Okay, so that's about the k part, kij part. And so similarly, we can calculate all the other k12, k13. Okay, and so let's also take, so B1 is nothing but your equation. What is that? It is nothing but your psi I times f. So this is the general equation here. But of course, there's a negative sign here because you take it onto the right side. And so putting it in our form, so psi I is just now we have here cos pi x by 4, cos pi y by 2, and f here is nothing but 2 by t, and dx dy. Okay, so if this is the thing, so what we have here is minus 32 by 5 by 4, 2 by t. Okay, so this is B1. And so similarly, we can also calculate all the other terms. So let me just put the matrix equation here. So similarly, other terms. So if I fill it up here, so that's what we have here. Surprisingly, these turned out to be 0 here. Q is the intensity of the loading, the uniform loading. So the third row is like this. Okay, so this is the set of algebraic equation in the form of matrix. Okay, there's one thing of interest is that only the diagonal terms are non-zero, all other off diagonal terms are 0. So this is because of the fact that the trial functions which are taken here or set of trial functions in such a manner that they are orthogonal. So that means that any product taken by itself will give you non-zero, but any other product taken of two different terms, so it will turn out to be 0. So that means that here A11, where we use the weighting function psi1 as well as the trial function psi1. So psi1 and psi1, so that will be non-zero. So whereas this corresponds to taking weighting function as psi1 and trial function as psi2. So when you take these kind of things, psi1 and psi2 here, so they all turned out to be 0. So this is something similar to your Fourier expansions. All right, so here you can continue here. So what you get here, if you solve this one, A1 is Q by T 2048 by 5 by 4, and A2 will turn out to be minus Q by T 5 to the power 4, and A3 So these are the coefficients A1, A2, A3 in the expansion for phi hat, right? So just to wrap up this problem, so we will just try to get or express the solution. So here the solution is in the form of phi hat. So we have psi naught 0, right? And then here, just expanding it. So we have A1 psi 1, A2 psi 2, and A3 psi 3. So each of these psi 1, psi 2, psi 3 were already given as the trigonometric set. And so you substitute them here and then substitute these coefficients A1, A2, A3 here. Then you have the solution for this one. So finally, just as a matter of interest, so we have this is corresponding to a membrane problem. So the maximum, so phi hat maximum occurs at x is equal to 0, y is equal to 0, and that turns out to be 2.003 2 by t. And the theoretical exact will be pi 1.082 2 by t. So these are just the comparison of an exact value with the approximate, which we got only using the 3 terms. So obviously there's a lot of difference between these two, and this approximation is very crude in that sense. So unless you take many more terms, you have to take many more terms, so the solution will not be good enough. Okay, so this has been taken just to illustrate the method of weighted residuals, and wherein we have taken rectangular domain, and the set of trial functions are such that they are trigonometric functions, and obviously the one important thing is that the function phi hat which we have taken is supposed to satisfy the given boundary condition before we put it into the weighted residual statement. Now let's move on to another very important aspect of this method of weighted residuals, is the weak form of this weighted residual statement. So what we're talking about is the weak form method of weighted residuals. So that means that the moment I say weak form, so what is the strong form which we meant? So in the sense that let's try to understand the original statement. If you recall, the method of weighted residuals is Wi into the residual so this is the original statement, this of course presupposes that this phi hat here, the approximation satisfies the boundary condition. Okay. So this phi hat, as you can see here, is being operated by L, which is a differential operator. So whatever, so phi hat is operated by L, the operator L, which is a differential operator. So L phi hat should not be identically 0 in omega. So this is very important, or undefined. It should not be completely identically 0 all over. That's number one. Number two, it should not be undefined. Undefined in the sense that a function, if it has multiple values at the same location, so that means that it is not properly defined. It should be unique. At any point, it should be unique. It should not be multiply defined. Or what we mean is that there should not be any discontinuity. Something like here. So if this is the function here, so the function should not have any discontinuity, and the function should be well defined. So then only it is we can do the differentiation. Otherwise, the derivative is not defined, right? So it should be well defined. The whole thing should be well defined, unique, and that means that this phi hat should be differentiable or continuous to the extent that L phi hat is uniquely defined. It's not, there should not be any discontinuity. So the requirement of phi hat here is controlled by the operator L, how big it is. If it is second degree derivative, then it should be differentiable twice. It should be differentiable twice, and then the continuity should be of that nature, right? So this is called the statement as given by L is as dictated by the governing equation. So what we would like to do is that we would like to reduce the L order, the order of L. Okay. So let us see how we do that. Okay. So how we do is that this looking at so we look at the term Wi L phi hat, and if you do partial integration, then what might happen here is that doing partial integration, so what will happen here is that Wi C, so this is some other operator C on phi, so this will be a integral on the boundary plus we will explain all these things more in these things will become clear as we take an example. So this term, so looking at this term, so if you do the partial integration, what happens here is that this will be integrated, L will become of a lower order, C, this is C and A are all difference operator. So what happens here is that this integral has become a boundary integral as well as it continues to be a domain integral on omega, right? So however, what you need to observe here is that this boundary term has L has become of a lower order C. And so similarly here in this domain integral, so the a differential operator has come on Wi, and then the phi will continue to have some amount of derivative here. Okay, the derivative will be less. So these B and as well as C are less than the L here. Okay, so here, so as you can immediately observe, this is fine, but then this is the one which we need to integrate phi hat. Now phi hat, which is the trial, which is the approximation, which includes a lot of trial functions, now are being operated upon by B, which is of a lower order differential operator. Okay, so compared to this one, here phi hat has been being operated by L, whereas here phi hat is being operated by B. So if B is of a lower order than L, obviously the continuity requirement on phi hat has been reduced, right? So here, so the operator B is of lower order compared to L, right? So that means that the requirement of continuity requirement of phi hat is of lower order. So this is an important observation which is having a profound effect on our method of weighted residuals. So that means that here again saying that B is of lower order, so B operating on phi hat, so that means that the requirement, the continuity requirement on phi hat is of lower order. Okay, so this is, so or we can even say that the phi hat can be a weak function. It can even be of lower order, called the weak function, or we say that this is the, compared to this original statement, now this statement is called a weak statement, okay, or weak formulation. So this is called, hence this is called weak formulation. So by doing this one, what we have done is that we are admitting the approximation function phi hat to be of a lower order, and so that means that the class of functions which we can take here are of bigger set. Okay, the phi hat is of a lower order continuity, so that means that the whole set of functions which we can take now are bigger set or have expanded. Okay, so that is the important part here. So this is a weak formulation. By doing this one, so we have expanded the set phi hat to be of a much larger class. Okay, so that's why this is a very important aspect of method of weighted residuals. So this offers the advantage that now we can look at a bigger set of phi hat. That's number one. Number two, by also incorporating here the residual due to the boundary term, then this will offer many other advantages of cancelling terms. So what I mean, so this is one advantage. So that means that phi hat admits lower order continuous functions and of a bigger class. Okay, say for example, here this requires a C1 continuity of first order continuity, whereas here this admits much lower order. So then if this is C2, if this requires C2, then this requires only C1. We will talk about that a little later. And so that means that we require only C1 continuous functions. So this weak formulation is that way, is our hands will be much easier to construct these kind of functions because they are of lower order nature. And so the question now is that, are we compromising? Are we compromising on the solution? So in reality, this is the stated problem. This is what we want. But then we ended up with this weak statement and then say that phi hat can be of a bigger class. So is that, are we getting at a solution altogether different from this kind of solution which we require? No. In fact, this set here of phi hat definitely contains this one, and this set here, okay, bigger set of functions definitely contains this function also which we require here. And then another important fact is that, is this another solution? No, it's not. Why? Because we are talking about linear set of functions, linear problems in which the solution is unique. So the solution which we obtain here and the solution which we obtain here are going to be same. Only thing is that we are looking at a bigger set of problems here. So we are looking at this phi hat is a much bigger class compared to this phi hat. However, the solution which we are getting here in the weak form will be the same as this one here, because we are looking at the linear problems, right? So that way, for all our engineering problems, so we are going to get the same solution. So there is no real compromise on the solution. We are going to get the same solution. However, now our constructing this approximation functions is becoming easier. Okay, so that's number one. And number two is we are also going to do another slight modification here so that the solution will become simpler. That is called incorporating the boundary terms. So now let's look at another aspect, important aspect. Another aspect here, so we are going to incorporate the boundary term into weighted residual statement. So what we mean by this one, why we have to incorporate the boundary term. Boundary term, of course, we know that the boundary condition is that boundary condition is this one, right? This is the boundary condition on phi hat. So both this strong form and the weak form up to now, till now, assume that phi hat is satisfying this boundary requirement, boundary condition. But however, not what we are going to do now is that we are going to relax this one. We are going to relax this condition. In what way? We are going to incorporate this term, okay, non-satisfaction of this phi hat into the weighted residual statement. So I think I'll stop here. We'll continue in the next class. Bye.